So we're told excess sodium carbonate is reacted with 7.76 grams of aluminum nitrate. What mass of sodium carbonate is expended? Well, one thing that should sort of stand out initially, because we just talked about it, is that you said excess sodium carbonate. If it's excess sodium carbonate, that means we really don't care about the sodium carbonate to start with. We do care about it to end with, because the question is, what mass of sodium carbonate is expended? We're going to figure out how much of it's used up, but the only one we really care about to start the problem is the 7.76 grams of aluminum nitrate. And so that's sort of what we're going to start with here. We know we're going to use that when we set up our factor dimensional analysis, set up our table and solve from there. And so to work with what we've got here, remember we said the first step was figure out what the products are going to be. And so we say the two things that are being reacted here are the sodium carbonate and the aluminum nitrate. It says sodium carbonate is reacted with aluminum nitrate. And so let's figure out what the products are. So we have sodium carbonate, that's a compound, is reacted with aluminum nitrate, that's a compound. And so if you look at your sheet that basically tells you what the reaction products are, is that compound plus compound. If you look at that, you'll see that is a double displacement reaction. And a double displacement reaction, you know that that basically is the anions switch places with respect to the cations. And so to work this out, we start off with sodium carbonate. And so we know sodium carbonate here, that's Na, and then carbonate is CO3. And so we've got that one. To balance the valences, you look up sodium. Sodium has a valence of +1. Carbonate has a valence of -2. That means you have to have two of these sodiums right here. And then we're going to add that to our next one, which is aluminum nitrate. So aluminum is Al. Nitrate, you look up on your polyatomic ion sheet, and you can see that nitrate's NO3. Now, aluminum, if you look at that up, that has a valence of +3. Nitrate has a valence of -1. That means we have to have a total of 3 of these nitrates. And so when these react, that the first piece it's going to make is we're going to start off with sodium as our cation, and we're going to go with nitrate as our anion. And so sodium we said was +1, nitrate's -1, so those balance. And then plus, and I am really running out of room today, plus our other one, which is going to be aluminum is the cation, and then plus the anion is carbonate, CO3. Aluminum, we said, was +3, carbonate's -2, and so to get this to work, we're going to put some parentheses out here. We have 2 aluminums and 3 carbonates. And so this is what we start with. So we have figured out what the products are. Would be, in this case, NaNO3, sodium nitrate, and Al2CO3, aluminum carbonate. Next step is to balance the equation. Write and balance the equation. We've already written out most of it. We just need to balance it here. So here we have 2 sodiums on the left, only 1 on the right. So let's go ahead and put a 2 in there. When we do that, however, that gives us 2 NO3s. We don't like that because on the other side we have 3 NO3s. That means we have to at least go to 6. And so we're going to get rid of this 2 right here. And instead we're going to have 6 NO3s. So we put a 6 right here. And so if we have 6 NO3s, that means we have to have a 2 out here to get this to work. But it also means we have to have 6 sodiums, because we have 6 sodiums on the right. We have to have 6 sodiums, 3 times 2 on the left. That gives us over here on the left 3 carbonates, 3 CO3s. And sure enough, we have 3 CO3s over on the right. So let's see, we have 6 sodiums, 6 sodiums. We have 3 carbonates, 3 carbonates. We have 2 aluminums, and sure enough, 2 aluminums right over here. And then we have 6 nitrates. So 3 Na2CO3 plus 2 AlNO33 yields 6 NaNO3 plus Al2CO33. Woo! We've written out our chemical equation. Next step is going to be to write out our conversion on this. And so let's go ahead and get that set up. So we're told that we start with the limiting reagent. We said the sodium carbonate is the excess one. It tells us that in the problem. So we start off with our aluminum nitrate, which is 7.76 grams. So we have 7.76 grams of aluminum nitrate. So aluminum nitrate, which we said was AlNO33. Okay. Now we're going to set up our table across here. And so we want to convert from grams of aluminum nitrate. And I'm just going to sort of abbreviate here so I don't run out of room. And we want to go to moles of aluminum nitrate. Okay? Now, to do this, as we sort of said before, is that what we're going to need is we are going to need to use the molecular mass. And so aluminum nitrate, AlNO33, we look at aluminum. Aluminum has a mass of 26.98, so we say 26.98 plus NO33, so that's 3 nitrogens. So plus 3 times 14.01, the mass of nitrogen. And then we have a total of 3 oxygens times 3, or 9 oxygens. So plus 9 times the mass of oxygen, which is 16. That gives us a mass of 213.01. And so we have a mass of 213.01 grams of aluminum right in here. For our next one, that's in 1 mole of aluminum. And so by doing this, that gives us a nice cancellation on the first one. That cancels out grams of aluminum nitrate. Grams of aluminum nitrate are gone. We have now moles of aluminum nitrate on top. We want to go from moles of aluminum nitrate to what we want, which is going to be moles of sodium carbonate. And once again, I'm going to abbreviate just to save some space here. Now, these numbers right here, remember we get from the coefficients. And so we look at sodium nitrate, and that's what we're looking for. Sorry, sodium carbonate. My bad. Sodium carbonate's what we're looking for. Sodium carbonate, that's right here. It has a coefficient of 3, and so we'll put a 3 right in here. For our next one, which is on bottom, that's moles of aluminum nitrate. And moles of aluminum nitrate's right here. That's a 2. And so we have this here. Once we've got that, that cancels out our next one, moles of aluminum. Those are gone. Now we have moles of sodium. And so while we got moles of sodium, it says what mass of sodium carbonate. And so we're now going to convert from moles of sodium carbonate to grams of sodium carbonate. And so to do this, we once again are going to have to figure out what the masses are. And so we look at this, we say sodium carbonate, Na2CO3. And so to work that out, we're going to say that sodium is 22.99 if you look on your periodic table, and there are 2 of those, so times 2, plus we have 1 carbon, which is 12.01, plus we have 3 oxygens, so plus 3 times 16, the mass of oxygen gives 105.99. And so we know in this case that the mass here is 105.99. That's what we get out of that. And so at this point, that cancels out our last one that we had, which is moles of sodium. Moles of sodium is gone, and that was in 1 mole right there. And so now, once again, we take out our calculators, and we're going to multiply it across the top and divide by the bottom. So 7.76 times 1 times 3 times 105.99 divided by 213.01 divided by 2 divided by 1 gives us 5.79. And so our final answer here that we get is 5.79 grams of what we're looking for, which was sodium carbonate. So NaCO3. Na2CO3. Sorry about that. It's Na2CO3. So Na2CO3, and that looks a little confusing there, but it's Na2CO3, sodium carbonate. That's our final answer for that. Okay? So one more example before we finish up here. And this one is going to be, if it'll let me, there we are. Potassium metal is allowed to react with 56 grams of iron 3 carbide to precipitate elemental iron. What mass of iron is precipitated? Now, once again, our first step here is to figure out what the products are. Here it says potassium metal is allowed to react with 56 grams of iron 3 carbide. So it sounds like that our 2 reactants are pretty obvious. It's going to be potassium metal and iron 3 carbide. But then it says to precipitate elemental iron. You'll see this word occasionally. And I want to sort of talk about this very briefly about what it means to precipitate or substance precipitated out. Is that when that's mentioned, basically what it means is that if you have a solution like this, you've reacted to things in a particular, say a test tube or something that's in a liquid, is that what will happen is once they start reacting, is that one of the things that's produced sometimes will not dissolve in the liquid that you had. And as a result, is that it'll sort of form little crystals that'll sort of form out in the middle of this. And those crystals will slowly sort of fall down to the bottom, and you'll be left with the precipitate that's down at the bottom of what remains of your solution here. And so when it says precipitated, that means that's one of the things that's created. that's going to be a product of that reaction. And so whenever it says that, sort of keep that in mind. That's the meaning of that particular term right there. So so back to our stoichiometry action. So potassium metal is allowed to react with 56 grams of iron 3 carbide to precipitate elemental iron. So first step is let's write out the chemical formula to figure out what the products are. So we said potassium metal. Potassium metal is just K. And then we're going to say that's going to be allowed to react with 56 grams, my bad, of iron 3 carbide. So iron is Fe. It's iron 3. That means that it has a charge of +3. If you look at your periodic table, you'll see that iron is normally either +2 or +3. This one is iron 3. Carbide ends in "ide," so it must be just carbon by itself. So it's just carbon right here. Now carbon, if you look at it, typically when it's on the negative side has a valence of -4. And so if we have iron is +3, carbon is -4, it must be Fe4C3, like that must be our formula. And now, once we've got that, let's see what this makes. This is element plus compound. And so element plus compound, a quick look at our predicting reaction product says that element plus compound can only be a single displacement. And so that means the potassium is going to come in here and is going to take over what's left here. And our format's generally going to be, if we have element plus compound, it's going to be then compound plus element. So the potassium is going to react with the carbon. So we have potassium and carbon. Potassium is, look at the periodic table, its valence is +1. The carbon is +4. And so that means we have to have, or -4, sorry. We have to have 4 potassiums. And then what's left over? Our poor iron all by himself, which is what it said. It precipitated elemental iron. Iron just as an element by itself. And so this is the reaction that we have here. Next step, balance the equation. So right now we have over on our left, we have 1 potassium, then we have 4 potassiums on the other side, so we would need a 4 out here, but I'm not going to put that 4 just yet. There'll be a 4 over on the left side, because look at the carbons. We have 3 carbons on the left, but only 1 on the right, and so that means we have to have a 3 right there, and by putting that 3 to make those carbons balance up, that gives us a total of 3 times 4, or 12 potassiums. So we have 12 potassiums to start here. Irons, we have 4 irons on the left, we have only 1 on the right. So we put a 4 over on the right to get this to work. So we have 12 potassiums on the left, 12 potassiums on the right. 4 irons on the left, 4 irons on the right, 3 carbons on the left, and 3 carbons on the right. We have this all nice and balanced at this point. So that's our first step. Second step, let's start with the limiting reagent. It says potassium metal is allowed to react with 56 grams of iron 3 carbide. You're not told how much potassium you have. You are told how much iron 3 carbide you have. And so that means we're going to start here with the iron 3 carbide. And so we have 56 grams of this iron 3 carbide. And once again, I'm just going to abbreviate this. You probably shouldn't abbreviate this whenever you're writing it out. I'm only doing it because of space issues on the screen. But it's a good idea to make sure you write out the whole thing, because otherwise it does get a little confusing when you do your mole ratios. It wouldn't be clear necessarily if you were doing the iron 3 carbide or just the elemental iron that's on the right. So I would suggest writing these out just as a general rule. We do want to convert from grams of our iron 3 carbide to moles of our iron 3 carbide. That did not show up. And so to do that, we are going to have to get basically what the molecular mass is. And so iron 3 carbide has 4 irons. A quick look at that tells you that the periodic table tells you iron is 55.85, so 4 times 55.85, plus 3 carbons, so plus 3 times the mass of carbon, which is 12.01. And so that gives a total mass of 259.43. And so we have down here 259.43. That's a point right there. And so that's going to be our grams here. So we have moles of Fe, and that's in 1 mole. At this point, that should nicely cancel out our grams of iron. Those are gone now. We have just moles of iron. And so that takes us to our next step. We want to get rid of moles of iron, because while the first step is to go to moles of what you start with, the second step is to go to moles of what you want. And here it asks us what mass of iron. So we're looking for just iron by itself. And this is one of the reasons why you don't want to necessarily abbreviate things the way that I have, because it gets really confusing here because I have moles of Fe over moles of, looks like Fe, when actually this should be just FeC3. 3C4. This is the whole thing written out. It just doesn't want to fit very well. And so to find these out, moles of Fe, what number is the coefficient of iron to find the mole ratio? It's 4. What about the coefficient of moles Fe3C4 of the iron 3 carbide? What number's out there? No number, so it's 1. So this is a 4-to-1 mole ratio. And so once we've got that, a quick look at this says that we'll now cancel out our moles of iron 3 carbide. That's gone. We have just moles of iron. The question at hand asks for what mass of iron, and so we're going to have to go to grams. So we want to cancel moles of iron. We want to go to grams of iron. Since this is just iron by itself, we look at the mass of iron. It's 55.85. So 55.85 goes in here. That's the number of grams in 1 mole. At this point, that's going to go ahead and that's going to cancel out our last one. Our moles of iron is gone. We just have grams of iron left. So to set this up, we say 56 times 1 times 4 times 55.85 divided by 259.43, and then divided by 1 gives us 48.2226. Now, significant figures, to start with, we only have 2 significant figures because we have 56 grams, so this will round just to 48, and so then our final answer here is going to be 48 grams of iron right there. And so that is how you do basically stoichiometry problems to set up.